All right, so let's finish up the notes where we left off. So using the fundamental theorem of calculus. So from topic 6.4, it illustrates the importance of anti-differentiation, integration. The fundamental theorem of calculus says that the integral from a to b of f of x is equal to big F of b, so the original function, right, minus f of a. So you take b, plug it in after you've integrated, and subtract that from f of a, where f is the antiderivative, big F. So let's evaluate each of the following definite integrals. So here we have a constant, and the integral of a constant is going to be a linear function. So if you recall, basically a constant does have an x with it raised to a 0. So when we integrate, you add 1 to the 0 and you divide by 1. So any integral of a constant becomes the linear function 10, that number with x, or any other variable that they're using, any other letter, from -2 to 4. Now that I have integrated, the next step is to use the fundamental theorem of calculus and basically plug in 4, so 10 times 4 minus 10 times -2. You do the math and you end up with 40 plus 20, and that will give us an answer of 60. So definite integrals, you'll always have a numerical answer at the end. All right, next up, we have a polynomial that has a radical function in it. So before we integrate, I do want to rewrite this to help me use the power property of integration. So this is going to be x squared plus x to the half from 0 to 1 dx. I'm going to integrate each of these separately. So that's going to be x, 2 plus 1 is 3, divided by that 3, plus half plus 1 is going to be 3 halves, divided by the 3 halves, which is the same thing as saying times 2 over 3. And that is going to be from 0 to 1. Now you notice that when I'm integrating a definite integral, a defined integral, I'm ignoring the c. All right, I'm not writing the c in, and I'll explain why in one of these examples. I'll show you why that's happening. So now I'm going to take that 1, plug it into the function. So we got 1 cubed over 3 plus 2 over 3 times 1 to the 3 halves. And then we're going to subtract, plug in 0. So 0 cubed over 3 plus 2 times 3, 0 cubed, 3 to the 3 halves. And of course, this gives us 1/3 plus 2/3. And this bottom one ends up being 0. So minus 0. Do the math. You got 3 over 3, which is 1. So the area under this curve from 0 to 1 is 1. And we can check that graphically if we needed to with a calculator. All right, part C. So here is an example of the trig function that you will have to memorize. I'm going to take this 2 out and bring it along for the ride as we integrate. Now the integral of secant squared is going to be tangent of theta. So that 2 is going to come along for the ride. And then the integral of secant squared is tangent of theta. And we're going to integrate that from -pi/4 to pi/4. And using the fundamental theorem of calculus, I'm going to leave that 2 on the outside. I'm going to multiply it at the very end. Tangent of pi/4 minus tangent of negative pi over 4. So that will give us tangent of pi over 4 is 1 minus tangent of negative pi over 4. Remember on the unit circle, pi over 4 is here, negative pi over 4 is down here, and that's going to give us negative 1. So we end up with 2 times 2, which is 4. All right, next up, before we can integrate this, let's see if we can simplify it algebraically. And we can. So the integral from 4 to 9, I'm going to break up the fraction. So when we have a single variable in the denominator, you can break up that fraction to each of the values in the numerator when you have a plus or a minus. So that's just basic algebra rules. So we got 1 over t to the half minus t to the half over t to the half. I'm going to do a little more cleanup. So that's going to be t to the negative half. You want to bring it up so that you can use the power property of integration. And then t to the half divided by t to the half is, of course, 1. So we're going to integrate each one of these individually, and we end up with t to the 3 halves divided by 3 halves, which is the same thing as times 2/3, minus the integral of a constant, like we did in example A, is going to be 1x, or we're just going to write, oh, it's a t in this problem, so we're just going to write that variable, from 4 to 9. You plug in 9 first, so we have 2/3, and this is the square root of 9 cubed minus 9. So that's plugging in 9. And then we're going to subtract, plugging in 4. So 2/3 square root of 4 cubed minus 4. Do the math. We've got 3 cubed is 27. Divided by 3 is 9. So that's going to be 2 times 9, which is 18, minus 9. Minus 2 cubed is 8. Times 2 is 16, divided by 3. So 16 divided by 3 minus 4. And then once you clean this up, did I do some math wrong? I think I did some math wrong. I did, because this is a negative half. So negative half plus 1 is 1/2. Yeah, so that literally changes my answer completely. And that's going to be t to the 1/2 divided by that half, which is times 2. Yeah, very different answer, right? So plug in 9 first. That's going to be 2 times the square root of 9 minus 9 minus 2 times the square root of 4 minus 4. So we got 6 minus 9 and 4 minus 4. So that gives us 0. And our final answer is going to be -3. All right. Remember, the integral of e to the x is just e to the x from ln of 5, from 0 to ln of 5. All right, so here I'm going to show you why I'm ignoring the c when it's a defined integral. So if we integrated this with the constant of integration, we would say plus c from ln of 5, from 0 to ln of 5. Now, when it's defined, you are going to end up with a numerical answer. So this is going to be e to the ln of 5 plus c minus e to the 0 plus c. So e to the ln of 5 is just going to give us 5, right? Plus c minus e to the 0, which is 1 plus c. So what do you notice happens to the constant of integration, the coefficient of integration? C minus c, because we are subtracting, according to the fundamental theorem of calculus to figure out the area, that will always get subtracted out and disappear. So our final answer is just going to be 4 plus c minus c, which is 0. So anytime you have a defined integral between two values, we have to remember that that c is going to disappear. It's still there, but we don't need to write it in because it does go away. So here is an example that you have to identify. Anytime you have x to the first power in the denominator, you have to remember that this, the integral of 1 over x, taking out the 3, is going to be ln of the absolute value of x. Just like the derivative of ln of x is 1 over x. The integral of 1 over x is ln of x. If you try moving the denominator to the top, you notice that when you try to integrate this, when you add 1 over negative 1 plus 1, you have a 0 here, but down here you also have a 0. And you can't divide anything by 0, it's undefined. So this is a commit to memory kind of problem. So when we take out the 3, let's integrate. We got ln absolute value of x from e squared, from 1 to e squared. Remember that 3 is going to stay on the outside till the very end. Don't ever forget those constants that you do take out. Minus ln of 1. When I know that it's going to be positive, you'll sometimes notice that I will not write these absolute values because I know e squared is always going to be positive, and I know that 1 is going to be positive. So when you have bounds that are not negative, you don't really need to write those absolute values. But when you don't, they have to be there. Ln of e squared is going to be 2, because that disappears, minus ln of 1, which we know is 0. So our final answer is just going to be 6. All right, so as we saw throughout topic 6.4 and 6.5, the fundamental theorem of calculus has interesting byproducts, right? So anytime you take the derivative of an integral when there's an x and just an x, our answer is just going to be f of that x. So that gets plugged in and you're done. But if one of the bounds is not x, if it's a function, you remember that you have to multiply it by the chain rule. So we can't forget that. So let's evaluate the following just to review, right? We go from 0 to x. Derivative of the integral from 0 to x is just going to be x squared plus 1. And here, the derivative is just going to be 5x minus 3. and we're done, right? The rule above, however, takes a bit of a turn when the upper limit is something beside x as illustrated in the example below. So if you remember, if the upper limit is not x, first we have to plug in that 5x squared into t plus 1. But then this whole thing is going to get multiplied by the derivative of 5x squared, which is 10x. All right, and I'll leave the example 9 for you. Or actually, let's use, since now we know how to integrate, let's integrate this and plug in our bounds and then take the derivative. So when you integrate 3t squared, this is technically, let's call this the long method, okay? You don't have to use this, but this is just to prove why the derivative of the integral is as we said. So let's integrate that first. So the integral of 3t squared is going to be 3t cubed divided by 3, which is t cubed. And the integral of 1 is going to be t. And we are integrating this from 2x cubed to 2. So now I've integrated the function. I am going to use the fundamental theorem of calculus and plug these in. So we've got 2x cubed plus 2x cubed minus 2 cubed plus 2. Let's clean this up. So as we are cleaning this guy up, we've got 2 cubed, which is 8, x to the 6th plus 2x cubed minus 8 plus 2, which is 10. And then the last step is, it says, derive that, right? So now we are going to take the derivative of that answer. So 8 times 6 is 72. X to the 5th plus 6x squared. And then, of course, the derivative of 10 is 0. So this would be our answer using the long method. Now, using the fundamental theorem of calculus and the chain rule for that, our short method should give us the same exact answer. So let's check. You basically just take that 2x cubed, plug it in, right? Three times 2x cubed plus 1, right? And then times that by the chain rule, which is the derivative of 2x cubed, and that's going to be 6x squared. Let's clean this up. We got 3 times 2 squared is 4x to the 6th plus 1 times 6x squared. And 3 times 4x to the 6th is 12x to the 6th plus 1. All of that times 6x squared. And then when you multiply 12 times 6, that is going to be 72x. What did I do wrong here? 2x cubed. Oh, I did something wrong right there, right? Because 2x cubed is not 8x to the 6th. It's 8x to the 9th because that's a power to a power. So here we end up with 9, and then once we derive it, we have 72x to the 8th. Now that makes sense. And that's why this is going to be 72x to the 8th plus 6x squared. So you notice that the answers are the same using either of the fundamental theorem of calculus examples. And that concludes 6.8. All right, good luck.